Hello everybody, welcome to the course VLSI Design Flow RTL to GDS. This is the 41st lecture. In this lecture, we will be discussing routing. In the earlier lectures, we had seen that the physical design is broken into simpler tasks which are shown in this figure, and in earlier lectures, we had looked into chip planning, placement and clock tree synthesis. And in this lecture, we will be looking into routing. Specifically, we will be looking at global routing, detailed routing and then post routing optimizations. So, first let us understand that what is routing. So, routing basically involves making physical interconnections between different components of a design, right. So, in earlier lectures we had seen that we have done the placement of objects. So, we have placed the large objects during chip planning and the standard cells during the placement, right. So, all the entities in our design, those are basically placed at appropriate places on the layout, right. Now, once their placement is defined, then we do the routing, and during routing what we do is that we create physical interconnections between different components of a design. So, these these components are connected using nets, right, in the net list. Now, using the information which is there in the given net list, right, the connectivity of the components is defined in the net list that we started with, right. Just to recap that in physical design what we do is that the physical design tools, they take input as the net list, then the STC file in which the constraints of the design are there, and also it takes the information about the libraries, right. And we have seen that there are two types of libraries. The first is the technology library that we saw in detail when we discussed logic synthesis, and the physical libraries which are typically in the form of LEF. Okay. So, these are three most important things that a PD tool needs. Additionally, we give information about the floor plan, the die size and other things, and the tool options and other things. Those are also the input to the physical design tool, and at the end of physical design we get a layout. We get the layout which goes to the foundry for fabrication, right. So, the net list is given as an input to the physical design tool, and whatever the connectivity is there in the net list, that connectivity is made by the router, right, by using various layers of metals and interconnecting them and so on, right. So, this is the routing is a very complicated task, and perhaps the most complicated task in the VLSI design flow, because it involves a large number of entities, right. So, if there are say billion instances, right, then you can imagine that how many connections will be there. It will be more than those number of instances, right. And therefore, since the number of connections or nets involved in a design is very huge, the making physical interconnections for them is difficult, right. And it is further made difficult because of various constraints that a routing tool must honor. And what are these constraints? So, these constraints are related to routing resources. So, we discussed that in in a typical IC, there are say 10, 12, 15 layers of metals, right. But still the number of metal layers and the routing resources is fixed, right. It is not that it has got infinite routing resource. So, given the limited routing resource, a router needs to find a solution, and that is not an easy task, right. Further, it has to honor the design rules that comes from the foundry, design rules, meaning that what should the spacing, minimum spacing between two wires of a given thickness and so on, right. So, those kind of design rules must be honored by router, and further it must also honor the timing constraints, right. So, we give timing constraints using SDC file, and those timing constraints must also be honored, and the signal integrity issues also come up when two wires are running in parallel, and because of the cross coupling capacitance, one signal impacts other signal, and therefore, signal integrity issues comes up, and the router needs to take care of those issues also, and therefore, the routing is a very complicated task, right. So, and therefore, we break down this routing into multiple smaller tasks. So, these tasks are, the first one is global routing. So, in global routing, we create the plan for routing, right, for each net. So, in this, when we are creating the plan, we are not actually creating the physical interconnection. We are not doing a layout for the wires, right. We are just saying that for this net, it will cross which all regions, right. So, it is in terms of routing regions, the connection, the definition of physical interconnections that is found or that is determined during global routing is in terms of routing regions, not in terms of wire layout. And then in the next step, that is when we go into detailed routing, the detailed routing actually decides the actual layout of each net in the pre-assigned routing regions. So, the routing regions was determined during global routing, right, and using that information, the detailed routing basically does the creates the layout of each individual nets in our design. And once this detailed routing is done, then we do some post routing optimization. So, there can be some problems in our design, we fix them or improve some QR measure like timing and so on. So, those are done after detailed routing. So, in this lecture, we will be looking at all these design tasks. So, first let us look into the global routing. So, in global routing, what is the goal? The goal of global routing is to provide complete instructions to the detailed router on where to route each net in the design, right. So, the global routing is basically creating a plan, right, and this plan will be further used by or utilized by the detailed router, right. So, the plan should be such that the detailed router ideally should not fail, meaning that there should be feasible solution which could be easily determined by the detailed router. That is the primary goal for global routing. It eases the task of finding a solution or finding a feasible solution for the detailed router. Now, during this global routing, what are the objectives that it must try to achieve? First is that it should maximize the probability that the detailed router can complete the routing, meaning that it should take decisions such that the routability of our design improves, right, or that the detailed router will not fail, right. That is the first objective and the most primary objective of a global router. Additionally, it should look into the total wire length and try to minimize it, and the total wire length is also some kind of measure for the routability. And then it should minimize the critical path delay, so that maximum operable frequency of our design can go up. Now, what is the desirable characteristics or what is desired of a global routing? So, global routing is basically used many a times in a design flow, though we are looking in detail at this point of time, but this global routing is used at multiple design steps, right. For example, even during synthesis, there are some flows in which we create some rough floor plan and do some rough placement and routing, right, and then assess the quality of logic synthesis solution and take some decisions, right. So, those are known as basically prototyping. We are creating a physical prototyping of our design by creating a rough layout of our design, right, and in those cases also this global routing is used, right. And during floor planning also we have seen that to assess the congestion of our design we can use global routing, and also during placement we can use global router to assess the quality of placement, and based on that it can change the solution and so on. So, since global routing is a kind of say rough way of doing a routing of our design, it should be very fast, right. That is what a desirable characteristics of global routing is. It should be very fast, a few orders of magnitude faster than the detailed router, right. So, that is why if it is fast, then we can use in early design stages also for getting some rough information that how the interconnect will look like, and based on that we can do some timing analysis or congestion analysis or take some decisions which will improve the QR of our design. Now, what is the routing model that is used, right? So, to make the global router fast, what we do is that we use some specific type of routing model, right. So, what we do is that we divide the routing area into rectangular grids, right. For example, suppose this was our layout, right, this is the layout, right, and this suppose that there are say 3 metal layers. In this case, I am just for simplicity I am assuming that there are 3 metal layers, metal level layer 1, metal level we can call it as M1, this is M2 and this M3. Then what we do is that we divide the layout area or routing area into rectangular grids, right, which is shown in as we have done here. So, there is a rectangular grid for each layer, right, we have divided it into rectangular grid. Then each rectangular region is called a global bin. For example, if we take this small rectangular region, this is a one global bin, right. Similarly, this is another global bin, this is another global bin, right. So, at the in this figure that we have shown here, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 global bins, right. Each individual small rectangular region is known as global bins or GBs that we have shown in this figure, right. Now, various tools, the various physical design tool can use various different kind of names for the same thing, right. For example, some can use the name as global tile or routing tile or say global cell or bucket, right, or even we are calling it as global bin, right. So, just for consistency let us call it global bin, but take a note that physical design tools might be using some other name for the same thing, right. So, now using these global bins which are built over the layout, we create a grid graph, right. What is a grid graph? Now, grid graph is also a similar type of as similar as a graph, right, as a conventional graph. It contains vertices and edges. Now, what are the vertices? So, vertices correspond to the GBs, right. So, in this case for the layer 3, there will be 3 vertices 9 vertices corresponding to 9 global pins, right. And what are the edges? The edges represent the boundary between adjacent global pins, right. For example, this is the boundary between this and this. So, we will have a edge, right. Now, we have discussed earlier that the connections or the routing that is done for interconnection in various layers that follow a preferred direction for each layer, right, and that is also taken into consideration while creating a grid graph, right. So, let us take an example like what happens, right. So, in this case there are say 9 vertices for first layer M, we are calling this as M1, M2 and M3. So, for M1 layer we have 9 vertices, right, 9 vertices, others are not shown. And then we have for the other M2 layer also will have 9 vertex, and for M3 also will have 9 vertex, right. So, corresponding to each global bin will have 1 vertex, and then we draw the edges. Now, how do we draw the edges or how do we create the edges? So, we create the edges by looking into that what is the preferred direction, right. So, we create edges between 2 adjacent vertices only if they lie along the preferred direction of routing. For example, let us assume that the preferred direction of routing is along the y axis for the layer M1 and M3, right, and for M2 let us assume that it is along the right. So, for the M3 layer we will have edges only along this, right. These are the edges. We do not have edge along this direction, which is non-preferred direction, right. Now, for layer 2 or M2 layer we will have edges only along the x direction, right, not along the y direction. Similarly, for layer 1 we will have only edges along the y direction, that is shown here, right, and so, right. So, we create edges along the preferred direction, and also we create edges between two vertices that lie vertically adjacent, right. For example, this global bin and this global bin, those are vertically adjacent, one is lying above the other, right, and therefore we create an edge for this. Now, what does this edge represent? So, this edges represent the vias, right. So, while making interconnections, we will have we might need to go from one layer to another, and for that we need to use these via layers or via edges, right. Now, given this grid graph, how does a routing of a net is done, right. So, we first is that we associate the pins with the proper global bin, right. So, for example, let us take that there is a inverter which is driving another inverter, right. These two inverters are driving, this inverter is driving the next one, and let us call that this net name is N, right. So, we want to create an interconnection for this net N, right. So, the first thing we need to locate that where are the pins are for this net. So, the pin is this, let us call this as Y pin and this as X pin, right. Now, we have already done the placement, right. When we have come to routing, we have already done the placement. Therefore, we know the location of this pin Y and X, right. Now, so on the layout, we know that, say for example, Y is at this location somewhere in this global cell. So, Y is here and say X is here, right. So, we locate the corresponding vertex. So, the corresponding vertex for this is this one and for this is this one, right. Now, to create the layout of the wire net N, what we do is that we find an optimal path in the grid graph that contains all the vertices of that net, right. So, in this case there are only two vertices because there are only two pins, right. So, we have to create a path between this point, this vertex and this vertex, which are shown in red, right. And how do we create this path? We create it using some optimality measure, right. So, we need to optimize it based on some cost measure and find a routing solution or for this particular net, right. So, the routing solution can be something like this, maybe it goes from this layer 1 to, or from this vertex to the next vertex, that is this one, right, and then it goes along this, then it goes along this, and probably then it goes to a layer up, then it goes through this and this, right. I am just showing one of the possible paths, right, it need not be optimal, right. So, the tool will find an optimal path, right, and this optimal path is basically kind of representing that what is the layout of this net, right. It is not exact layout of the net, but it is the path that the layout of the net will be traversing, right. So, the actual layout will be created by detailed routing, not during global routing, and we are discussing right now global routing, right. So, during global routing, the solution for the routing solution for this net will be as shown in this figure, right. So, this not be optimal, but what I am just showing for the purpose of illustration that what it could be a routing solution, right. Similarly, it will be doing a routing for other nets also, and then the entire design, right. So, and for entire all the nets in our design, the global router will find a solution. Now, when a net crosses the boundary of 2 GBs, then we say that the net utilizes the corresponding corresponding edge, right. For example, we saw that we created this was the starting point, this was one y pin and this one was the x pin, and we created a layout, right. We created a path on this grid graph, right. So, when this happens, right, then if we consider, say for example, this edge was used by this net, right. So, when a net crosses the boundary of 2 GBs, right, when for example, in this case it is crossing the boundary of these 2 GBs, right, then the corresponding edge, so the corresponding edge is this one, right, this one which I am highlighting, this one. So, the corresponding edge is said to be utilized or used, right. So, note that one particular edge can be used by many nets, right. Why it can be? Because this is this global bins that has been created, it contains many routing resources. For example, it may contain many tracks of wires, right. So, one edge that I am showing here, for example, this edge, right, it is actually physically representing many tracks of wires that can be laid out, right. It is not only one track, it can be many tracks, and therefore, each edge in our in the route in the grid graph that can be used by many nets, right. So, the number of nets utilized by an edge, that is known as use of that net, or we can also call it as the demand of that edge, right. So, we say that an edge is used by a net if the net crosses that edge, right. Now, if there are multiple nets which are crossing this edge, then we say that this edge has got an use of that many nets, right. For example, suppose this edge was being used by 3 nets, right, it was used by 3 nets, right. Then we say that the use of this edge E, let us call this edge as E, is equal to 3, right, because 3 nets are crossing that, right. Now, we also need to be careful that what is the capacity of the edge, right. If one particular edge is used many times, maybe say 1000 times, that is not a good routing solution, because later on detailed router will not find sufficient number of tracks in which we can lay out say 1000 nets, right, and therefore, detailed routing will fail. Therefore, while doing this global routing, the router should also understand that what is the capacity of the edge, right. So, capacity quantifies availability of routing resources for an edge. It somehow relates to that how many tracks are available for routing by the detailed router, right. So, now this capacity is also called as supply, right. So, whenever we use a net, we say that the demand has been created for that edge, right. And when there are many resources available for an edge, we say that the supply is increasing, right. So, the routing blockages limit the capacity, right. So, note that we are doing routing after doing power planning, and also we have the power planning was done during the chip planning stage, right. So, when we did power planning, some resources, say top level routing resources or routing layers, those were used for power grids, right. Therefore, those are not available, right. And there also we are doing this routing after we have done clock tree synthesis, and therefore, some routing resources has been used by the nets that are related to the clock nets, right. And therefore, when we come to this routing, we are basically routing the data signals, right. The clock signals is already routed, the power lines are already laid out, right. Now, we are left with data signals which are mainly targeted during the routing, right. So, while computing the capacity of an edge, and router should also be aware of where the routing blockages are there, or which are already utilized routing resources. So, the capacity will come down, right. And it also depends on the layers and the design rules, right. For example, that if we say if we have a thinner wire, or thinner wire, meaning that its width is small, right, and if the width is large, right. Now, if depending on the width, the design rule says how much spacing should be there and so on. And therefore, if we use a more wider wire, then the capacity of an edge decreases, right. So, yeah, depending on the layer and also the design rules, like what should be the spacing between one track and the other, that is decided by the design rule which comes from the foundry. Therefore, the capacity computation by the when the global router is computing the capacity, it should also take into account the layer for which it is computing the capacity and also the design rules, right. Now, what should be the relationship between capacity and edge, right? We said that it found the tool found a path, right? A global routing tool found a path from this point to this point, something like this, right. Now, while finding this path, what should the constraint be on the routing path? So, one of the most important constraint is that it should honor the capacity constraint, meaning that the use of or utility of an edge, that how many nets are using a particular edge, that should be less than or equal to the capacity, right. It should be less than or equal to capacity. If it is more, then it is likely that detailed router will fail, because we have routed many nets through an edge and there are not sufficient routing resources or tracks available for detailed router to do the layout or create the layout for that net, and therefore, the capacity constraint will be violated, and we measure it using a quantity which is known as overflow, right. So, we define overflow as use minus capacity, right. If use is greater than capacity, right. So, if we are using more than the capacity, then there is an overflow, right, and this is not a good condition, it is an overflow, and how much the overflow is, it is defined by the difference between that. For example, suppose there is for an edge, the use of that edge was say 5 and the capacity of that edge was say 2, then what is the overflow? The overflow in this case will be 5 minus 2, that is 3, right. If the use is less than, or equal to capacity, then we say that the overflow is 0, because in that case the use is not more than the capacity, that is a legal condition, and therefore, overflow is defined as 0 for those cases. And then if there is not overflow and we want to quantify that which routing path is better than the other, then we use a measure which is known as congestion, right. Now, how do we define congestion? We define a congestion as use divided by capacity. For example, if the use of a net was 4 and capacity was 6, right. So, the congestion will be 4 by 6. Now, in another solution, if say the use was say 5 and the capacity was still 6, then the congestion measure will be more in the second situation, right. So, we can quantify that how much utilized, what fraction of the resources are being utilized by looking at the congestion measure, and typically we try to reduce the congestion in our design by spreading out the routing or use such that it is fairly equally used or evenly used over the layout. Now, what does the global while finding the path, for example, the path that is shown here, what will the routing tool will try to look into and try to optimize, right. So, the first thing the tool will try to attempt is to route all the nets in our design with overflow of 0, right, meaning that if the overflow is 0, then probably the routing the detailed routing will succeed, and that is the primary goal of global routing is to make the detailed router succeed to find a feasible solution, right. Now, while trying to attain it, say overflow is equal to 0, if the tool needs to take sacrifice other QR measure, for example timing, it can do that, right, because the more important for the tool is to find a feasible routing, right. So, for example, if the tool is finding a path and this path was broken or it was having a not available routing resources, all were used up by other nets, right, then it will probably look into, say, other path through this, right. It may take a longer path, maybe it may find a longer path, or it can take a detour to between various endpoints of a net to avoid overflow, right. And if it is doing a detour or taking a longer path, then probably other QR measure like wire length, delay, those will be suffering, right. So, but the routing tool can take those kind of decisions. Now, what are the challenges for global routing? So the first or the biggest challenge for a global router is to do the things or perform global routing with minimal runtime and also maintain accuracy. Now, what do we mean by accuracy? Accuracy of the timing measures, the other QR measures with respect to the detailed router, right. So, what is global routing trying to do? Global routing is trying to basically simplify the problem for the detailed router, right. And therefore, it should be the solution that the global router produces, right. It should very much be correlated with the detailed router, and that is maintaining both things, that is runtime, lower runtime and accuracy with respect to detailed router higher. Maintaining both of them is a challenging task, right. So, how can we improve the runtime? One of the easiest way is to, say, increase the size of the global bins, right. Now, when we increase the size of the global bins, what happens? The number of bins that needs to be tackled by global router, that decreases, right, because the layout area is fixed. We are increasing the size of the global bins. So, the number of global bins that needs to be tackled by the global router, that comes down, and therefore, the problem gets simplifies for global router and its runtime can come down. But what effect it will have on detailed router? The detailed router will now see a bigger bin, right, and therefore, the problem of, or the complexity of the problem for the detailed router, that increases, right. And therefore, in effect, if we increase the size of global bin, the problem of routing is transferred from global routing to detailed routing. It is actually not solved, right. Therefore, just by increasing the global bin size will not help, right, because the accuracy will suffer. And why do we want to maintain the accuracy of the global routing with respect to detailed routing? So, the reason is that, see, that what we are trying to do is that we, at the global routing stage, we are trying to we are trying to find some feasible solution for the detailed router by finding some paths based on global bins, which can be further utilized by detailed routing. And also, what we are trying to do is that we are trying to anticipate problems that will be seen by the detailed router, right. For example, suppose detailed routing problem is much difficult than the global routing problem, and therefore, the runtime of detailed router is significantly higher than the global routing. So, it may happen that when we run detailed routing, it may take, say, 12 hours to run, and at the end of 12 hours, the detailed router simply says that it could not find a feasible solution, right, then that is a very bad thing, because our time and design time, effort and computation time has gone waste, right. So, what we do, what we typically, the responsibility of global routing is that anticipate the problem that will be seen by detailed router, and if there are issues, for example, congestion or overflow and those things, those problems should be flagged during global routing itself, and a designer can then take a corrective action, right. For example, if some perturbation in placement is required, then it can be done, and so on. So, those kind of design changes can be made by looking at the solution of the global routing. And therefore, the global routing should try to model the problem such that it is similar to the detailed routing problem, right. So, what I mean to say is that the global routing should model, say, the routing resources in a fashion which is similar to what is seen by the detailed router. And to do that, what the global router needs to consider is the design rules that a foundry has basically imposed on the layout, right, or related to the interconnects, right. Or if those things are considered more at a fine grained manner, then the global router can be the solution found by global router will be something which will be similar to that seen by detailed router, and the design closure can be speeded up, right. Now, let us look into detailed routing. Now, what are the goals of detailed routing? So, the goal of detailed routing is to determine the exact layout of each net, including all the attributes of the wire segments such as width and location. So, now in detailed router will create the entire layout for a net, right. For it will create, so it will break down a net into multiple wire segments, and for each wire segment, what is its width, what is its location, those will be determined during detailed routing. And what constraints detailed routing must consider? First of all, of course, the connectivity that is defined in the net list, that must be honored. There shouldn't be any extra open net or any short circuit net, right. So, the connectivity should be exactly same as in our given design, as in our given net list, right. And then the design rules also must be considered. So, those will be coming in from the foundry, and the detailed router must consider the design rules. And in addition to that, it must look into the timing constraints, the signal integrity issues, and of course, the runtime, right, because the runtime of detailed routing is very important, because typically it takes very large runtime, and therefore, using some techniques, for example, multi-threading and others, the detailed router tries to control or keep its runtime lower. Now, in a typical advanced process nodes or industrial designs, there are the number of metal layers is large, it may be 10, 12, 15 and so on, and therefore, there are lots of routing resources available even over the cell, right. So, the cell may be using a few routing resources for the internal connections, right, but the upper layers are all available, and therefore, over the cell routing is done during the detailed routing, right. Now, how does the detailed routing work, right. So, it work using the similar as, or it creates a routing grid, or what we call as detailed routing grid, which is similar to global routing grid that we just saw. However, here the granularity of those routing grid will be much finer than what we saw for the detailed router. Now, in this case, the tracks with uniform spacing, right. So, in the detailed routing, what the data structure or the abstraction of tracks are used. Now, what are tracks? Tracks are basically metal lines, and so the basically the detailed router tries to find out which all tracks to be used for making connections for a given net. Now, these tracks are typically uniformly spaced, right. So, we create these tracks with a uniform spacing. This spacing is same for all of them, right. And these spacing is known as the routing pitch, and what should be the spacing of these routing tracks, right. So, this will come from the foundry, and why do we create these routing tracks and why the router works at the abstraction of tracks? It is because it allows us to do automation. So, it allows uh, the use of tracks for routing or doing detailed routing simplifies the algorithm of detailed router, right. And therefore, most of the tools use this kind of detailed routing tracks as an abstraction for carrying out detailed routing. Now, what should be this routing pitch? An important the routing pitch is the spacing between two tracks, right. This is the spacing, or we call it as the routing pitch. Now, what should be this routing pitch, right? So, routing pitch is defined as the minimum spacing allowed in the technology, right. Now, during routing, what do we typically want? We want to pack these wires as compactly as possible, right. We want to basically we want to make our design or layout as compact as possible, right. Then we can save on the area, right, die size, and we can save on cost and also improve the yield, right. So, typically we want to do the interconnections or create routes as packed as possible, right. So, and ideally, if you want to pack the wires as close as possible or as tight as possible, then where does the constraints come from? The constraints come from the foundry. The foundry says that if you have this much width of the metal wire, right, the metal segment, then the next segment must have at least this much spacing, the minimum spacing. Those kind of information will come from the foundry, and the router needs to honor them, right. So, those are coded in as design rules, right. So, the foundry gives us design rules in which the information is that what should be the minimum spacing between two wires of a given width, right. And given this, the design rules, still there are many choices available, right. For example, what we can do is that the routing pitch we can define as the minimum distance between two lines that is allowed by the technology. For example, suppose this is the minimum width of the line, right, that can be drawn in a given technology, and for that minimum width we say, and the foundry says that the spacing should be, say, W, right. Now, we can make the tracks W distant apart, right, all these are W, W, W and so on, right. So, we can do this kind of, or we can create tracks based on this information, but what will be the problem with this? The problem with this will be that it is too aggressive and it will create a lot of DRC violations, meaning that there will be design rule check violations. Why can there be a design rule check violation? The reason the violations can come, for example, if we want to insert a via here, right. For example, this line was going and then it has to change the layer, either go up or go down, right. Then we have to insert a via. Now, if we insert the via, there are different rules for via versus line, right, and therefore, there will be a kind of, so when there is a via and there is a line, the spacing between via and line will be required somewhat more than what will be the minimum width between two lines, that is W defined by this, and because of that there will be design rule violations. Now, to fix it, what we can do is that we can, if we want to insert a via, we will leave this track and use the next parallel track, but then this track which we have left, that is being unutilized. We are not packing as efficiently as possible, right, and therefore, this may not be a good choice line on line as the routing pitch. Other thing can be done is that we can consider say via on line, right. So, the foundry will define that when there are two vias adjacent, what should be the minimum spacing, and based on that we create routing pitch, right. Now, this will save us from the DRCs, but the problem is that are we packing all the wires as closely as possible? The answer is no. Why it is no? Because there will be many lines where there are no vias which are in the adjacent, right. There are just two lines, right, and in that case if there are just two lines, we could have made them closer without having any violations, which we are not doing, and therefore, making a track or the grid graph based on tracks with via on via spacing, that is also not a good solution, it is too conservative, right. Typically, what we can do is that there is in the design rule, we have that between a via and the line, what should be the minimum spacing, right, and we can take that as the let us call it as W dash, and we can create the tracks based on the width of W dash, right, and therefore, whenever we need to add one via, right, we need not make any we need not leave any unused space, right, or unused track, we can have it on the same track, right, and therefore, there we have allocated space for the vias, right. But when we need two vias, like in this situation, whether we can either skew them in space or we can leave one extra line, but those situations where two vias should be exactly at the same horizontal space, right, at the same space, that may not be that case may not arise too often, and therefore, this line on via spacing may be more optimal or is maybe a good trade off. Now, using the routing model that we just discussed, the tool will find a feasible solution if it exists or if it can find, right, using some heuristics. So, the routing problem is an NP complete problem or a difficult problem, and there are various heuristics that are used by the tool, and in this course we will not go into the algorithms of routing. If you are interested, you can look into the books which are dedicated to physical design algorithms, right. So, after the routing is done, right, after the detailed routing is done, then some optimizations will be required or will be done to fix issues in our design, right. So, till the time we have not done the routing of the signals, we are just estimating that what could be the interconnect delays, right. Based on, we do not even know the layout of the interconnects, and therefore, based on some heuristics and some assumption of that how the wire will look like, the delay of interconnects or the parasitics of interconnects are computed and delay is estimated. But after we have done the routing, right, then we have the exact layout of the wires, and we can extract the parasitics, and based on that we can do the timing analysis, right, which will be much more accurate than what we did during synthesis or in the earlier stages of the design flow. And once we do the timing analysis, we may find some violations, and then we need to fix the problem. For example, we can improve the timing by say gate upsizing, buffering, automatic manual rerouting, automatic or manual rerouting, we change some routes to improve the timing for the critical paths, or we can do wire widening also if the routing resource is available to improve the timing. Then we can also think of improving the power dissipation in our design. For example, we can do gate downsizing for the paths where the timing is not that much critical. So, in there we can reduce the size of the gates, and as such we can improve the power dissipation or decrease the power dissipation. But the increase in the delay will basically not impact the final QR of our design. Also, we can remove buffers on the path where it is not, which is not required, right. And we can also do some what is known as we can change the cells based on its footprints, right. So, now we say that in our library there will be say an AND gate, 2 input AND gate, and there will be another 2 input AND gate which has got the same footprint, meaning that its layout is exactly the same, right. And therefore, if we replace one with the other, it will not matter on the layout, right. But internally the transistors here may be say this way may be a low power transistor, meaning that it may be having a VT of high VT transistor, or it can be high performance transistor. It can contain high performance transistor where the VT or the threshold voltage of the transistor is low. And if the some gate is not on the critical path, we can use low power cells in there and we can save the power, right. Then we can also or after routing we should do signal integrity analysis and then fix issues, for example, by increasing the distance between the wires, right, or maybe upsizing the victim driver, right, or downsizing the aggressor driver of the aggressor driver, which is actually injecting noise into the other victim net. So, we can do those kind of optimization after we have done the routing, right. In addition to the optimizations, after routing we need to also consider some other effects, right, or other problems that can be there in our design. One of them is antenna effect, and we had discussed earlier that when a gate dielectric and the gate terminal of a transistor is directly connected to lower level metal M1, it can lead to antenna rule violation, and this gate oxide can be prone to antenna effect induced gate damage, or what we call as also known as plasma induced gate damage, right. So, this gate terminal is connected to M1 line, and if this area is large or this length is large, then there probably can be a antenna rule violation. So, if there are antenna rule violations, how can we fix it? So, one of the techniques is to say that we do the routing, major portion of the routing in the upper layer of the metals, right. For example, instead of doing the major portion of the routing in M1 layer, we are using an upper M2 layer where the wire goes where most of the routing is done, and we go from M1 to M2 layer in the very close to the gate, right. So, we avoid long M1 lines directly connected to the gate terminal. Instead, we use higher layer metal M2 for routing. And the other way to fix this problem, suppose this M2 layer was not available, right, that routing resource was already used up, then probably we can use a jumper, right. So, M2 layer here is just used as jumper. We have M1 layer, it goes to M2 layer, and then to M2 layer it goes down through a via again to M1 layer. So, most of the routing is still done using the M1 layer, but there is no direct connection between this M1 layer segment, this one, and there is a gap, right. And therefore, the charge if it gets accumulated, it will get accumulated through on this part, and the gate will not be damaged, right. This is how we can fix antenna rule violations after routing, or even during routing we can take decisions. For example, in this case we route it on M2 layer, so that we need not get an antenna, or we avoid getting antenna rule violation. Now, after routing we can also look into some reliability issues, right. For example, reliability issues arising due to VR defects. Now, what are these VR defects, right? So, we have discussed earlier that whenever there is a say one metal and another metal, we want to go from one metal to another metal for creating routes, and we insert vias, right. Now, these vias are very small structures, and these are prone to defects because of mask misalignment, right. For creating vias we use multiple layers of mask, and if there are some misalignments, there can be defects in vias, right. And also these vias can be prone to thermal stresses, and because of that vias can fail, right. So, if there can be open circuit defects in the vias, and if we are lucky, then those problems will be caught during testing, and then we will be having yield loss, and if we are not that lucky, that problem will be found by the customers, right, as reliability problem. Maybe say after after few operations of the circuit, there comes a VR defect and the circuit loses its functionality. So, that is more or that is a worse situation, right. So, to avoid this kind of situation, a popular method is to add redundant vias, right. So, we add, instead of one via, we have say 2 vias. So, if even if one fails, the other will provide the connection between 2 layers, right. Now, how can we insert redundant vias? Let us take an example. Suppose there is a metal layer M1 and M2, right, and these are connected by these vias, right. So, there is one layer M1 going like this, M2 in orthogonal direction and the via in between them, right. Now, if we want to insert another via, where can we insert? So, there are 2 ways to do that. One is what is known as on track via. On track via. In this, what we do is that we extend one of the lines in non-preferred direction, right. For example, this M2 was in horizontal direction, in this direction. We extend it slightly to a non, so in this case we are extending this M2 layer along this direction for a short distance and make a connection, right. Similarly, we can do for the M1 layer also. So, this is the M1 layer, right, this is an M1 layer. So, M1 layer is below M2 layer. So, it is going slight. So, we are extending along non-preferred direction, right, along the horizontal direction, and then we create a via here, right. So, these vias are on track via because we are using the same track as that, right. So, for short distances, it is usually allowed that the routing is done in non-preferred direction, and those are basically known as jogs, J-O-G-S, jogs. So, these, for example, in this case, this yellow line or M1 line is used as a jog here, right, in this from here to here, right. And in the other case, this M2 line is used as jog from here to here, right, this is the preferred direction is horizontal and it is running in vertical direction, M2 is running in vertical direction from here to here, and it is used as jog, right. We can also have off track via, right, we can have off track via. So, in off track via, what we do is that we extend this line, right. So, we extend this line M1 along the preferred direction and extend the M2 line, right, along the non-preferred direction. So, the preferred direction is this for M2 line, it is going in this direction, and here we have added a redundant via, right. Similarly, what we are doing in we can do is that we can move, we can carry along this M2 in the preferred direction, right, and M1 along non-preferred direction, right. So, the preferred direction of M1 is vertical, but it is run for a small length along the non-preferred direction, and here we have this redundant via, right. So, this is how we can insert vias to improve the, or we insert redundant vias to improve the reliability of our design, right. Then we can also tackle some manufacturability issues post routing. So, what are these manufacturability issues? One of them comes because of CMP. So, remember that when we are discussing how we make interconnects, right, we discussed dual Damascene process, right, and in that process we need to do chemical mechanical polishing to planarize the interconnect and the dielectrics, right. So, for planarizing, we actually use mechanical polishing, right, and what happens is that if the roughness varies over the layout, then there can be irregular topography, right. What we mean by this is that suppose this was our side view of our chip, right. So, in this region lots of metal is there, right, and in this region there is only interlayer dielectric or SiO2, right. Now, when we planarize it using chemical mechanical polishing, right, CMP is chemical mechanical polishing. So, when we do chemical mechanical polishing, then SiO2 being a softer material, more planarization will be done in that area, and we will have an more polishing will be done in this area, and we will have an uneven topography, right. Now, to if there are irregular topography, then it can lead to yield loss. And to fix this problem, what we do is that, suppose in our layout there is metal layer widely used over this portion, and in this region there was not enough metal layers used, right. And there it may create this problem of irregular topography in this region if we don't have extra any metal there, right. And therefore, to solve this problem, what we do is that we add dummy metal fills, right. So, what we do is that if there is on the layout, some portion of our layout is not having enough metal, in that portion we fill extra metal which is not doing any functionality. It is just to make the roughness of the chip evenly distributed throughout the chip, right. It should not be that some area is very soft, some area is very hard, and so on. To make the uniform hardness of a given layer, we insert extra metal fills in the area where there is not enough metal. But once we do this kind of metal filling, we should be aware that this extra metals will actually change the capacitance because of the mutual coupling between the other interconnects. So, these extra metal fills, those are not actually carrying any current, but they are existing in the layout, and therefore, the potential profile of the interconnects that are in vicinity and they are carrying the signals, that may change, and because of that the timing profile of our design can change, right. So, we should be aware that if we are doing this dummy metal fill, right, dummy metal fills, or these are also known as CMP fills, because these are targeted for CMP or solving the problem related to CMP, it is also known as CMP fills. So, whenever we have done CMP fills in our design, then we should again do extraction of the capacitance, especially the mutual capacitances, and also carry out timing analysis again, right, to ensure that after dummy metal fill insertion our timing is still closed, right. Now, if you want to look into more on the topics that we discussed in this lecture, you can refer to this book, right. Now, to summarize, what we have done in this lecture is that we have looked into global routing, detailed routing, and some optimization that we can do after the routing, right. Now, once we have done the routing and say we have done the timing analysis, our design is clean, and the implementation process is a kind of finished, right. Now, our design, our layout is created, all the entities are placed, the routing has been done, all the required interconnections have been made over the layout, and in that sense our implementation phase has completed. The design is now ready to be taped out, right. Our layout has been created for our design and it is ready for tape out. But can we do the tape out, right? So, we can do, but since this is the last opportunity to check whether there is any problem in our design, we should be making it, or we should be doubly sure that our design is perfect or is behaving correctly, right. So, after we have done this we are done with this implementation phase, we do another round of physical verification and sign off before doing the tape out. So, in the next lecture we will be looking into physical verification and sign off steps. Thank you very much.